All right.
Hello, everyone. Welcome to another TVS colloquium. Today, we have the pleasure of having Chaini with us. He's a PhD student at University of Delaware, and he will tell us everything about distant metrics for time domain astronomy. So please, Sid, take it away.
All right. Thank you, Priscilla, for organizing this and having me over. I'm Sid Chaini. I'm a PhD student at the University of Delaware. And today I'm going to be talking about how we can leverage distance metrics for machine learning in time domain astronomy. And I'll also be talking a bit more about a Python package and a method we developed called DistClassiPy. And yeah, without further ado, let me get into it. Here's the outline of my talk. I'll start by introducing and giving an overview of what time domain astronomy is. Then I'll talk a bit about machine learning and how distances are important in machine learning. Then I'll talk about DistClassiPy, which is the package we developed, and how we use that to classify variable stars in the ZTF. And finally, I'll end up with a Python demo just to show you how it works. So, time domain astronomy is the subfield of astronomy related to how cosmic objects change with time. And this change is typically over human time scales. So something like seconds to days to years. And typically we can think of uh, objects which are like within time domain astronomy to fall in these three rough categories. So the first one is variables. So an example would be something like a pulsating star. So variables are events that, so sort of events that alter the brightness of some object, either periodically or episodically, but they sort of persist. Then we have something called transients. So these are events that generally fade over time. So an example would be a supernova, for example. And finally, we have moving objects, which is where the position changes with time. So something like asteroids. And I'll be mostly talking about the first two kinds of objects. So, for example, here's a pulsating variable. And because it's the brightness that's changing with time, we end up looking at these things called light curves, which basically just show how the brightness changes with time. And Rubin is almost here. And the era of Rubin can be sort of thought as a revolution for time domain astronomy. And this has mostly been driven by newer surveys, which take repeated observations of the sky, which has mostly been driven by advanced data storage and the advent of CCDs. And so over here, for example, I have a plot which shows how the data volume collected per night has changed over the past 2 decades for different surveys. And I'm particularly interested in the last two of these, so ZTF and LSST. So the Zwicky Transient Facility can be thought of as a precursor survey to the Rubin Observatory's legacy survey of space and time. And we can see that even here, there's an order of magnitude of difference in the amount of data collected. And in terms of stellar light curves, that boils down to ZTF having observed around 3 billion stellar light curves in its lifetime, which actually just got extended by 1 year. So now ZTF is going to run another year, actually. But apart from that, Rubin then is expected to observe around 17 billion stellar light curves by its end of life in around 2035. And so that's a lot of data, and that's a great time to be doing time domain astronomy. But to sort of harvest this data, to do any science with this data, we have to be able to classify these objects. And so, for example, variable stars have really key science roles in making population maps, and then sort of looking at the distribution of how stars are distributed in our galaxy and getting a distance estimate to them, and also to sort of be able to map dark matter to an extent by looking at different stars. And so apart, and then transients, on the other hand, are also great distance indicators, but at the extragalactic scale. So something like a Type 1a supernova is really useful for cosmology. And apart from that, they're just great testing beds to explore extreme physics and so on. And so in this image here, I just have the popular, the cosmic distance ladder, which shows how the distance scale, the method of getting distances in our universe changes as we go to different distance scales. And so lots of really important science cases. But at the end of the day, if we want to do anything with these objects, we have to be able to classify them. And typically, this classification would be done by spectroscopy. So by looking at a star's spectrum, we can look at different absorption lines in that spectrum. And so that can tell us much more about what its chemical composition is. And then we can look at its physical properties like color, temperature, size, and so on. And so in this image here, you can see the classic stellar spectrum uh, classification. So that's OBAFGKM. And so spectra are also useful for transient events. So for example, for a supernova, it gives you a really good indicator of redshift and in turn distance. So ideally, we would want to get a spectrum for all of our sources, and that would be perfect. But unfortunately, there are a few fundamental issues with spectroscopy. So, firstly, is that spectra take time. And that is because when compared to photometry, which is just taking images of the night sky, which is what Rubin and ZTF also does, and Rubin will be doing. For spectra, you need to have an integration time where you're collecting light for the order of hours. So, just as an example, I was speaking to Fed about this, and she mentioned how for around a 20th or magnitude supernova, you would need around 15 to 20 minutes of calibration time, followed by around 45 minutes of integration time. And so uh, that's still much more time than how much a photograph takes, especially when you look at surveys like Rubin, which will take a wide field photograph. And so spectra take time. And that's not only it. So you also need bright objects. So in the example I mentioned, the order 20, the magnitude 20 supernova, that's still on the brighter end of what Rubin will be observing. So Rubin will be going up to 24, 25, and potentially more magnitude. And it's just going to be very difficult to get a a spectrum for these stars, at least with the telescopes we have today, like a 4-meter telescope, for example. And finally, because um, inherently spectra take more time, to get a spectrum for all of our objects would involve having lots of telescopes. And we just do not have that many large telescopes. And so now the question is, can we use photometry to get a classification? So can we use light curves? Can we look at these light curves and instead of taking the spectra, and can we get a classification based on this? And if we can do that, that would still save us a lot of time, just in terms of, for example, the calibration time I mentioned earlier. So you could skip out on that and sort of choose what transients or variable stars you're interested in, and then get a spectrum for a subset of all those objects. So you don't have to get a spectrum for everything. You can choose what objects you're interested in and then focus on those objects. And that just makes that's a bit easier than getting a spectrum for everything. So so here are some example light curves from ZTF and the LSST, which is still not out yet. So the left one is real data. It's from the ZTF data release 15, and it's an example of a variable star RR Lyrae. The right one is a plot of from the plastic data set, which is a simulated LSST data set. And you can notice how ZTF is mostly the ZTF works in three filters, of which one of them is not so great. So mostly two filters, G and R, while while LSST will be observing in six filters. And so just with that, we have a lot of different color information in the light curves itself, and that's what makes photometric classification possible. This difference in colors. But like I mentioned, the issue is that we cannot uh, observe these objects spectroscopically. And the other challenge in the Rubin array is that the high volume of data requires fully automated methods for classification. And I think it's really important for us to rely on photometric classification with machine learning and design machine learning methods that sort of keep our science goals in mind. So let me briefly talk about what machine learning is. So machine learning refers to a broad range of statistical algorithms that learn patterns from data. And in the context of time domain astronomy, it's important for us to automate classification of light curves, among other things like dimensionality reduction and anomaly detection and so on. And so here's this image actually generated with an AI with a text to image generator. So in this image, you can see how it's trying to classify a light curve into different bins. But anyway, so machine learning, great. We want to leverage that for a few different tasks. And typically, the common algorithms used for light curve classification include something like a tree-based classification scheme. So two examples of this classifiers are a random forest or an XGBoost, a gradient boosted decision tree. And so what these tree-based algorithms do is they look at different features of the data and then make cuts based on these features. So you end up with a decision tree that looks like something like this. So this example is not on variable stars, it's on planets, but you can still sort of get a rough feel of how the decisions are being made. But decision trees on their own are not really very strong and tend to overfit a lot. And what that means is that they do not work that well. And so typically we look at an ensemble of trees, aka a random forest or a gradient boosted tree. And that makes it much more powerful and it's more accurate. But that does lead to a loss in interpretability because then you have 50 decision trees like this working together and you don't know why. So each decision tree on its own is not that great, but when combined, they work really well. But that still has the issue of not being so interpretable because why does this tree work better and why does this tree not work better and so on. So it's still, although we still know what's going on, it's still difficult to get scientific interpretability out of it. And so these tree-based methods typically require feature extraction, which is that in case of a light curve, you extract different features of that light curve, so numbers that tell you something about that light curve, and we feed that into these algorithms. On the other hand, the more modern slash new common approach right now are neural net based approaches. So especially with something called recurrent neural networks or transformers, they work well for sequential data. And they're really great because what they allow us to do is that they allow us to skip this feature extraction process where we can just pass our inputs, our light curves directly to a neural network and it will classify it. And so the issue with neural nets has been that they have been much more difficult to train because you need large networks and then you need a large data set and then you have to run it and train it for a long time. But we've still been getting better at that and they work fairly well. But the other key issue with neural nets is that they are not very interpretable. And although there has been a lot of advancement and research being done into making more interpretable neural networks, we are still limited by the fact that at the end, if we have a neural network with us that's pre-trained and we give it an example, so we give it a target and we ask for a prediction, we don't really know why the neural network predicted it the way it did. And like I said, it's getting better, but it's still not good enough for, especially if you want to get scientific understanding from it. And finally, there's also distance-based methods. So an example is the k nearest neighbors. Um, which is what I have in this image here. And so how they work is that they also require feature extraction from the light curves in this example. And then what k-nearest neighbors does is that once you have a target point, the green circle here, it looks at the three nearest neighbors if k is equal to 3. And then depending on how many of those nearest neighbors are from what class, it classifies the green point. And so the really good thing about this is that it's very, very interpretable because you have this feature space. You can look at where the object lies in this feature space. But its main limitations are that, firstly, it does not work as well out of the box. Um, for most tasks, and that is because it's very difficult to use parametric models. So the parameter in this case would be the distance um, out of the box to capture nonlinear correlations, to classify nonlinear problems, basically. And so what that means is that out of the box, k nearest neighbors is difficult to use. And then the other issue is that it's also very computationally intense because you have to calculate distances of every target point with multiple training points. And so it just blows up computationally. And for large data sets, it's really, really slow. Um, but yeah, so like I mentioned, these methods, distance-based methods, get a bad rep based on the fact that they're parametric and these parameters don't work so well, while something like tree-based and neural net methods are not parametric, and that's why they are more preferred. Um, but hopefully by the end of this talk, I'll convince you that we can still choose suitable parameters for distance-based methods. And so DistClassiPy is our method which we developed. So this has been inspired by k-nearest neighbors, but it's a bit different. And what we focused on was trying to leverage the use of different distance metrics. And so I'll talk a bit more about this in detail. But a lot of this work is now like based on this paper we published a couple of months ago. And for more details, you can read that and refer to it. And essentially, what we found out was that we were able to classify light variable star light curves accurately, fast, while having results that were more interpretable and the ability to customize the algorithm. And I will talk more about each of those points. But before I do, let me talk about how DisClassify works. And so this is the algorithm from the paper. But instead of going through this over a slide, let me just demonstrate this visually. So for example, if I have two features, so in this case, just for this example, I'm looking at, say, the period and the amplitude, and I'm looking at these two classes, Cepheids and RR arrays. And so then my training step consists of calculating the medians and the standard deviations. And so we end up representing the class by this centroid point. And then and that's it for training. And then once we have a test object for prediction, we calculate the distance of this test object to all our classes. And then we scale this by standard deviation. So what this does is that it helps capture nonlinear uncertainties better. So what we're doing is we're measuring how many standard deviations away the test object is from the Cepheids. And in this plot here, that's the reason I sort of removed the axis, because now it's um, basically the dimensions of the Cepheids is different from the dimensions of our array. But it's still a simple calculation problem. And finally, we choose the nearest class as the prediction. And so, like I said, this is a fairly easy and interpretable method, uh, and not a lot of computation is happening. But the key insight we wanted to look at was that when we calculate this distance, what happens if we change the kind of distance being calculated? And can we use the properties of different distance metrics, to help us classify our light curves better? And I just want to say that this was an example, just for an example's sake, I showed you a simple problem in 2 dimensions, but we apply this method for arbitrarily many dimensions. So as much as 100 plus dimensions. But let me talk about what a distance is. So a distance is a quantity that tells us how similar two objects are. And mathematically, a distance metric just has to obey these three axioms. So a distance metric is a function that obeys these three axioms. So the first one is the identity of indiscernibles, which means that the distance between point 1 and point 2 is 0 if and only if they are the same points. The second axiom is symmetry, which means that the distance from point 1 to point 2 is equal to the distance from point 2 to point 1. And finally, the third axiom is the triangle inequality, which just means that the distance from point 1 to point 2 plus the distance from point 2 to point 3 is more than the distance from point 1 to point 3. And so as long as we have a function, a formula that obeys these three axioms, we have a valid distance metric. So, for example, the distance we know and love the most because of its use in a real day-to-day world is the Euclidean distance metric, and it is a valid distance metric because it obeys these three axioms. But if we swap it out for something like the Clark metric, you can look at how it has a different form from Euclidean, but because it still obeys these three axioms, it is a valid distance metric. And so we can also try and get a uh, we can also try and visualize these distance metric spaces by looking at the loci of a central point, say 5, comma 5. So we know that the in the Euclidean space, the loci are just concentric circles, and the distance increases as you go away radially from the central point. And in terms of, so in case of the Clark distance metric now, you can look at how the distance metric, the visualization looks very different. So it's still concentric, the loci are still concentric, but they appear to be squished in some, in a way. And so essentially you can get a sense of how the choice of the distance metric is warping the space and allowing nonlinear features to be captured. And so what we did was we looked at 18 different distance metrics. Um, so these are distance metrics that have been defined in literature for various purposes. And we wanted to see if we can leverage each of these distances properties and to see if that can help us classify light curves better. And just to give you a sense of how different a lot of these distances are, so something like the meal distance metric, for example, um, it only changes in one dimension in one direction here, but it's not changing in the other direction at all. While something like the Chebyshev distance metric, instead of concentric circles, they look like the loci look like concentric squares. And so that has a lot of fun different um, reasons behind it. But essentially, we have these bunch of distance metrics, and we want to see if they can help us. And in this paper, we looked at 18 distance metrics, but I've also been working on adding more distances to our package, and I will talk a bit more about that in the demo. Um, yeah, and before I move forward, I just want to say that this visualization is in 2 dimensions, just so that it's easy for us to get an interpretation of the space. But this is happening in n dimensions, so it's arbitrarily many dimensions. So now let me talk a bit about the work we did on applying it to ZTF light curves. So we looked at this data set, this catalog by Chen et al., which consists of 780,000 variable stars in 10 classes in two filters, G and R. And this is what the rough classification hierarchy looks like. And to develop and test this methodology, we looked at three different classification problems within this hierarchy. So firstly, we looked at a one versus rest classifier of eclipsing algols versus everything else. Then we looked at a binary classifier of these two rotating variables. And finally, we looked at a multi-class classifier classification scheme of these four pulsating variables. And I won't talk too much about pre-processing here, but essentially what we did was that we firstly extracted features from our data using LSS's module. Then we dropped redundant features and rebalanced our data set. And that left us with around 500 objects per class, with 31 features per object. And what we found out was that DistClassiPy performed as well as the state of the art, which in this case is a random forest. So for all the three classification challenges given here, our performance was within the error bars of a random forest benchmark. And one thing I want to mention here is that how the distance metric changes for the best distance metric is different for different classification problems. And so this just goes back to how distance methods can work well if you have the right parameterization, which you can get by choosing the right distance metric. So great, we were able to get a good performance as good as a random forest. But what do we Oh, wait, yeah, sorry, I forgot to talk about this. So, one thing you can see is that the binary classification case here is not as good as the other two. And the reason for that is that the two rotating variables you're looking at, RSCVNs and BY Draconis, their physical processes are different. Um, so they have different underlying processes. So RSCVNs are typically binary systems of one F or G star along with the K star, while BY Draconis is generally a single late state star KRM. And they have different physical processes behind them, but observationally, they end up looking very similar. And they just end up like looking similar because they end up looking at light curves between zero point 0.1 and zero point 0.2 magnitudes. And they are typically accompanied with a slow period and a phase change. And so this makes classifying these two classes of rotating variables difficult. But we still know that even the random forest struggles with this classification problems. But this classifier was still within the error margins for this problem as well. And so yeah, what we found out was that broadly, a DistClassify can be as good as a random forest for each of these problems. So what is different with DistClassify? So firstly, it's much more computationally efficient. And so here I have a plot of compute time as a function of data set size. And the random forest, so DisClassify is between 10 to 100 times faster than a random forest. And this difference is even more apparent for larger data sets. So just to give you a sense of numbers involved, so DisClassify with the Clark distance metric, for example, took around 0.16 seconds for the largest data sets, while something like a random forest took 13 seconds for the same problem. So around 100 times faster. Um, but that's not all. So DisClassify is much more interpretable, and we can see that based on 2 points. So firstly, like I mentioned, because we know what features are being used, we it's easy to keep track of why a particular classification works the way it works. But secondly, we also looked at something called sequential feature selection. And what that does is that we can reduce the dimensionality of our feature space from 31 to just something like 3 dimensions. And we found out that using these three features still gives us a really good result with the Canberra distance, for example, in this plot. And what that allows us to do is that just by reducing the amount of features we're looking at, it now is even more interpretable because we can keep a track of it's easier to keep track of 3 features than 31 features. And so these features also change for different distance metrics, and different distances work better with different features. Finally, and I think this is a key thing which DisClassify does, is that it's very easy to tailor the method based on the kind of objects you have. So uh, basically, depending on your object, there is a distance metric that works best for that object. And let me illustrate this through this plot I have here. So what I did was I split my test data into four quantiles based on this feature, the period. And so what we can see here is that let's look at something like Canberra. So uh, it performs really well on objects from quantile 1. So these are objects that have a low periodicity, but it does not perform as well with objects from quantile 4. So that is objects having a high periodicity. On the other hand, if we look at something like the meal distance metric, it works not so well for low periodicity objects, but works really well for high periodicity objects. And so, what that allows us to do is that we can sort of choose the distance metric that works better based on how our test object looks like. And we can do this because you don't have to retrain because the distance metric, the measure is only chosen during prediction. So once you have your centroids, you can change the distance metric being used, and um, you can use a different one for different objects without retraining. And I will talk a bit more about this in the demo as well. But before we move on to the demo, let me just quickly talk a bit about some ongoing work I'm looking at. So I'm also trying to expand this to work with transients, and I'm looking at transients from simulated LSST data. So transients, it's 6 filters, but that involves different feature extraction methods because a lot of these feature extraction methods don't work well for so many filters. And so I'm looking at how we can use a few different feature extraction methods like a Gaussian process or a neural process with an autoencoder, etc. But basically, what it means is that if you can have a good way of extracting features from your light curves, you can use DistClassiPy. The other thing I'm looking at is anomaly detection, which is that suppose I have this distribution in my features and I have an anomaly in my data set. So I want to find out something that does not belong to any of these classes. And what we can do is then we can measure the distance of this anomaly from each of those other classes and see how far away it is from all of them. So in case of the Canberra distance here, if we use the Canberra distance to measure the distance of this anomaly to everything else, we can see that it's still pretty separate from the other classes. But now if we swap out the distance metric being used, so if we look at something like the mean distance metric, that just helps it isolate it even more. And so, yeah, that is some ongoing work I'm working on where I'm looking at how the choice of distance metric can help isolate the anomaly better. Um, and DistClassiPy is open source, and it's based on the scikit-learn API. So let's move on to the demo. So if you would like to join along, you can scan this QR code or look at this URL. But yeah, let's look at this Jupyter notebook I prepared. And so uh, So let's first start by installing this classify, and I'm installing this particular version. So in case there are new versions, this tutorial will still work whenever you try this out. And let me just also clone my GitHub repo so that I have all my data set here. So what I'll be looking at is that I'll be looking at some features of light curves provided by the ZTF source classification project, and you can look at this paper for more details. Um, so I just cloned my GitHub repo, which has my data here, and perfect. So let me start by importing some prerequisite modules as well as DistClassify. Um, Perfect. So now, let's start by looking at some different distances. So, like I mentioned, I added even more distances to this classify. So we looked at 18 distances in the paper, but now there are 43 built-in distances within DistClassiPy, and we can visualize this distances by this uh, function I wrote here. The AI recommendation is wrong. Um, so something like the Euclidean space, for example, looks like this. Oops. Yeah. Uh, and then you can swap it out for something like the Canberra distance or the Challenger distance. So cool. Let's look at the data set in a bit more detail. So, like I mentioned earlier, I'm using data from this ooh, okay, seems like it's down. But this data set by the ZTF scope project, and I already downloaded them to this and sampled them to have a sort of a clean version of it here. So let's read that in. And so this is what it looks like. So these are the different features, and these are the different labels. And just to see how many classes we have. So I have 1,000 objects of each of these four classes: Cephids, Delta Scoties, RR Lyrae, and RR Lyrae type C. And like I said, this is just a small sample from the whole catalog, from the whole Zenodo file, just so I have a demo to give. Um, And for the sake of simplicity, let's focus on three features, just so instead of dealing with these hundreds of features, let's look at three different features, which I think still encapsulate a lot of different information. So the first one is the inverse von Neumann ratio, which is the ratio of correlated variance and variance. And so that helps detect non-randomness and tells us in some way about the periodic behavior of the light curve. The other feature is norm peak to peak amp, which is just the amplitude between peak to peak. So it tells us about the brightness of a light curve. And finally, we have the Stetson K coefficient, which is another statistic that tells us about the shape of the light curve. So let me type these in. Cool. And just to see oops, there's a typo. Just to see what the features look like, we can do a pair plot, and that will show us the distribution of each of those features. So each of this plot is Stetson versus the von Neumann ratio, Stetson versus the peak to peak amplitude, and so on. And you can see that it's not so, especially the Cephids can still be separated fairly well based on the von Neumann ratio, but the other classes are still not so easy to separate. Um, and so let's now prepare our data set. So let's start by creating our variables x and y. So x is the input to the machine learning algorithm, and y is the labels for this data. And let's split it into training and test sets. So now let's move on to the distance metric classifier. So the distance metric classifier is based on the scikit-learn API. So it follows this convenient pattern which you might know of. So it has a fit method, a predict method, and so on. And it's also fairly easy to use. So we can do something like DCPy or distance metric classifier, and we can uh, fit it on our training set and our testing on a training set. And that means that it's now fit to the data. And then we can predict on the X test. And during prediction, we can also provide the metric. So the default one is Euclidean, but we can also, and let's look at what the performance with this metric looks like. So the Euclidean distance metric does not perform so well in this example, but we can swap it for something like the Hellinger, for example, and that's a bit better. And we can also change this method to look at uh, the distances themselves. So this is the same score, but now my CLF has this data frame, and that just tells me the distance of each of my test object to each of the four classes clusters. And so this can be really useful to see how close an object is to other classes and how far away it is, and for potentially anomaly detection later on. But the last thing I also wanted to touch on was also an ensemble distance classifier. So one thing I mentioned about was splitting the data into quantiles. And so what the ensemble distance classifier does is that you can create uh, this classifier, and it automatically splits the data set into quantiles and then chooses the best distance classifier for that quantile. So to split it into quantiles, you just have to provide it which feature you want to split it on. So I know that the von Neumann ratio looks like a good feature to split my data set on. And so let me split my data set based on that. So that's what the feature index means. And let me split it into 6 quantiles. And then uh that's for later. I got fooled by the AI recommendation. So let me also provide a random state. So uh the quantile is chosen during fitting. So let me fit it based on X train, Y train, and let me split my data set into 6 quantiles. And so this takes a bit more time because it's sort of going through all possible distance metrics for each of these 6 quantiles. And then what it does is that it looks at what the best metrics per quantile are. And so you can see that for different quantiles, we have different metrics that work better. And so we can um, use this on our test data set. And the AI predictions are pretty wrong. I'm sorry about that. Um, what this does is this goes us predictions once again, and let's look at the scores again. So you can see that using this, we slightly improve on our performance by just using the Hellinger metric, and that's because this is now incorporating multiple distances inside it. And we can also look at what the best metrics per quantile were, and also the quantile scores itself. And let me drop duplicates for better for a better table. And so yeah, this is what the ensemble did. So essentially it split the training data into 6 quantiles, and then it measured performance on each of those quantiles for each of these distance metrics, and then it stitched up different distance metrics for quantile based on how well it performed. So anyway, that's it. This is something that's really useful, I feel, especially if you can look at what the values for the distances are. That can provide a really good resource to sort of get a feel for where it lies in that space. And I think it's just allows for a lot of things you can do with this. And this distance is based on the distance metric I passed here. So if I passed something like Canberra, these values would change, as you can see. So anyway, that's the tutorial, and that's all for my talk. So thank you so much for listening. If you would like to read the paper or look at the package, you can look at this QR code. And that's it. Thank you so much.
Thank you, Sid, for this very interesting talk and very pedagogical demonstration. So I hope many people get the chance to play with this. So
Thank
yeah,
you.
thank you.